Welcome everyone to the fifth SEMLA webinar. I hope you enjoyed the previous webinars edition very much, and I hope you will enjoy this one as well. So if you are joining SEMLA for the first time, maybe allow me to briefly introduce what SEMLA is about. So SEMLA is a forum that aims to bring together researchers from both software engineering community and machine learning community to reflect and discuss about the challenges of engineering machine learning-based software systems. We have been running SEMLA for 3 years now, and this is the team behind organizing SEMLA. So we are faculty for Polytechnic of Montreal, Professor Adam, Professor Antonio, Professor Cheng, Professor Foucault, myself, and Professor Nayede. So this year edition is a series of webinars given the current pandemic situation that we're in. So we had a very interesting program this year. You have attended, I hope, webinars from Radibu, Chris Kastner, Dang, and Diego Oppenheimer from Ahlgren. And today we have a very exciting webinar ahead of us from Professor Mark Alman from Facebook. So Professor Alman is now a full-time research scientist at Facebook London, working on Facebook web-enabled simulation system, which is what he will be talking about during the webinar. But before that, his team was part of the deployment of Sapiens to test mobile apps at Facebook, which is actually a product that came out of a startup that he co-founded in 2017 called Magic. On a purely scientific academic background, Professor Markman is very well known for starting the search-based software engineering research domain, and his research work is well-renowned and have been recognized with many prestigious awards, including IEEE Alan-Lins Award and ACM Outstanding Research Award. With that, I will let Professor Alman start the session. Just before we get to that, I want to remind you that you can use, as in the previous webinar, the QA box to input your questions, and you can also vote on your favorite question. So after the presentation, we will relay the question to Prof. Alman, and we will start a discussion from there. For that, please, Mark.
Hello, everyone. Thank you very much, Fudse, for that very kind introduction, and thanks to the organizers for inviting me. I hope you can now see my slides. Fudse, can I just ask you to confirm that you can see the slides, just so I know that we're...
Yes, I can see this.
Great. Thanks very much. So yes, thanks very much, everyone. So this talk is scheduled to fill a 1-hour slot, but my hope is that I'll only be talking for 35 or 40 minutes, and then that will allow plenty of time for questions. I believe you can put your questions in the QA session on Zoom, and then at the end we can go through them. There's a voting process, as I understand it. Okay, I may not be able to answer all your questions, but I'll do my best. And the other thing is, at the end of the talk, I will also be mentioning, in case you haven't already heard about it, that we have a funding call out on web-enabled simulation, the topic of this talk, and the deadline for that is the 15th of July, so there's still time. It's actually a very light touch process. You only have to write a 2-page proposal, so although the deadline is only in a few weeks, it's really very light touch, and it shouldn't take you too long to put in an application, so there's still really plenty of time. So what I'm going to talk about today is web-enabled simulation. It's Facebook's DubDub project. We call it DubDub because, as you'll see, what we're doing is we're simulating a subset of DubDub. My name is Mark Harmon. As Fudse mentioned, I'm a research scientist at Facebook. That's my main job, and it consumes most of my time, but I'm also a part-time professor at UCL, where I've been a professor for the last decade. And I've been an academic most of my life, and in the last 4 years I've been working in Facebook on teams that tend to bring together research and engineering practice. And what I'm going to talk about today is published in a paper that goes with this talk. The paper is actually the keynote for the genetic improvement workshop, which is coming up at ICSI next week. And the co-authors of the paper are my really wonderful colleagues in the London probability team. The team has grown a little bit since we wrote the paper, so this isn't the full list of people who are on the team, but I want to start the talk by acknowledging that everything I'm going to talk about now is the work of this whole team in London Probable T. Our goal is essentially to combine machine learning and software engineering, to use machine learning to make software engineering better. So it's machine learning for systems. So it's very well suited to the topic of this webinar. So the context for our work on web-enabled simulation is that on a social media platform, most people spend their time doing nice things and use the platform to connect with each other and to share content and to keep in touch. It's been particularly valuable at this time of COVID-19, when people really are relying on various forms of social media and other kinds of platforms like the one we're using now, like Zoom, to connect with each other and to stay in touch with loved ones. But it's not only good behavior. People being people, bad things can also happen on such platforms. And with such a large number of people using the platform, that's a serious concern. We want to reduce and tackle harmful behavior on our platform, particularly things which contravene our community standards. In this talk, I'm going to focus on scamming type behavior, and in particular, this relates to bot crawling. So the focus for the talk today will be scamming. The examples I use to illustrate will be based on scamming, but I hope you can imagine how the technologies that I'm going to be talking about could easily be applied to other kinds of harmful behaviors, and to modeling these and to tackling them. And the other thing I want to stress is that what we're talking about here is a project that we started a little under a year ago, and it started as a research project, and we're trying to develop it out. At this point, we have research prototypes, and some of the things I'm talking about are actually running now, but it's a work in progress. This is a project that we think of as a big bet to try and build a simulation of what real users can do on the real platform. And so it's a long-term gigabet project. So the starting point for our project is the Facebook infrastructure itself. And just to be clear what I mean by Facebook infrastructure, what I mean is all of the databases and data warehouses that contain the social graph and all of the entities and attributes of people on the social graph, and the processing itself, the functionality that essentially delivers all of the products to the customers. Now, this infrastructure is big. In software engineering terms, it's one of the largest software engineering endeavors that mankind has undertaken. It's hundreds of millions of lines of code, and just the apps that you use to connect to the back end are tens of millions of lines of code. And you can imagine that there are considerable scale challenges here. But simulating such a beast is not something scientifically that we've really encountered before. Certainly not where you try to simulate the actual infrastructure rather than making a model. So the idea of web-enabled simulation is that we actually use the web infrastructure itself as the platform on which we build the simulation. So we make bots that simulate users using Facebook infrastructure, but those bots actually operate on the real infrastructure itself. So bots perform actions like sending messages to each other, looking at each other's profiles and so on, subject to all the usual privacy constraints. But what they're doing there is they're performing these actions through the real infrastructure. So when a bot sends a message to another bot, it's going through the same code stack and backend that your message would go through if you sent a message to one of your friends. And similarly, when the bots make observations from the platform, they're making the same kinds of observations that a normal user would see in the normal course of their use of the platform. So the important thing about web-enabled simulation is because it's on the real infrastructure, there's an opportunity here to be much more realistic than other simulations. Contrast this, for example, with a simulation of an aircraft engine. It's not practical to build a simulation with a real aircraft engine, but software is this unique engineering material that means that we can build the simulation, which is itself software, out of software using the software that we're simulating as the platform. And that gives us a huge amount of extra realism, but a whole lot of extra scientific and technical challenges. So our bots are rewarded for being bad to other bots. They're essentially simulating harmful behaviors between bots. I should stress at this point that any and all interactions on the DubDub platform are between DubDub bots. So although it uses the real infrastructure, these bots are isolated from production. So how are they isolated? Well, first of all the actions they can perform and all the observations they can make are carefully constrained by construction. Secondly, we have an interaction mechanism layer, which I'll talk a lot about later on in the talk, because we use that as a basis for optimization, and that also mediates their communications with the back end. And we also essentially have a belt and braces approach, so the bots are also subject to the same privacy constraints, and we use those to isolate them as an extra check. So the bots use the real platform, but they're completely isolated from production. And we want the bots to simulate the kinds of harmful behavior that can happen on a social media platform. So in today's talk, I'm going to focus on crawling type behaviors. So the bots are rewarded essentially for exhibiting crawling behaviors that may be harmful. So let's take an example with scamming. So to the bot, the infrastructure at Facebook looks like a social graph. And a node in that graph is a user, and an edge is a friendship relation. There are all sorts of other edges between users, but we're going to focus on the friendship relation in today's talk. So we put our bots into the social graph, and suppose this is a completely innocent bot, but this is a less innocent bot with an intent to scam. Then it's going to try and search to try and acquire possible people to scam, people in this case, of course, being bots. And the interactions it makes with other bots may tend to make it move in certain directions through the social graph until it finds a potential other bot that it is going to try and scam. And our job is to understand this, to model it in our simulation, and to do two things. One is to stress test the existing infrastructure and classifiers whose job it is to catch this kind of behavior, to make sure that it can't happen. This is particularly important when somebody lands a new change to the code where essentially the classifiers are seeing an unknown scenario. So we have to, it's an extra way of checking that those classifiers work. And as I'll talk about later on in the talk, we also search for mechanisms which will tend to reduce the ability for bad actors to do harmful behavior while tending to allow normal users to behave normally. So in this case, we want to prevent a scam attempt on the platform by inhibiting the ability to crawl and find scam targets. So we train these bots. How do we do that? Well, there's three ways in which we train the bots, and they're increasing sophistication, and all three of them give us value in different kinds of scenarios. So the most simple of all is basically a rule-based behavior. So we simply, it's a good old-fashioned AI, as I think it's known to its friends. So essentially, we just set out a set of rules. So one way in which bots may traverse the graph is essentially a depth-first graph search. At each point in that search, the bot can choose some friends of friends to go to, so essentially crawling through profile friend lists. And when no friends are visible anymore, then the bot backtracks. So friends may not be visible because privacy constraints mean that the bot can't see anything, or as we'll see later on, it might be the mechanism that we're going to impose to try and prevent bad behavior means that there are no visible friends, and then the bot has to backtrack. So that's the simplest possible way of training a bot. Essentially, it's very simple-minded, rule-based approach. Next in sophistication would be a supervised machine learning approach. So we have an inordinate amount of data on real trajectories taken by real people on the platform, including some that we consider to have exhibited behavior that we would consider contravening our standards. And so we can use that to train our bots in supervised machine learning to essentially emulate or imitate the behaviors that we're interested in trying to model. So in the supervised machine learning approach, we collect anonymized data. So it's anonymized. I just want to stress that, and it's what we're doing is we're learning generalized patterns at scale. So these are aggregated patterns. We're not emulating a specific user, we're emulating the statistical properties of a whole class of users. And so we're training the bots to imitate reality, essentially, using supervised learning. And at the most sophisticated end, we can use unsupervised machine learning. So in this situation, we simply define a reward criteria, what it means for the bot to achieve a harmful behavior. And the environment issues these rewards, but we don't tell the bot how to behave. We just use reinforcement learning to essentially guide the bots in their choices. And all three of these have been implemented in our platform, all three of these approaches, and mixed variants. So one that's particularly interesting, I think, is a combination of the rule-based and supervised learning approach. We could talk about that in the Q&A if there's interest. Of course, the unsupervised machine learning using reinforcement learning and the combination of that with supervised learning puts this very much in the intellectual and scientific wheelhouse occupied by AI-assisted gameplay. And so a lot of the research that's in that area is also very relevant to what we're doing. So we train our bots to crawl and to perform bad behavior on each other. So the actions that bot performs, say a bad bot that's trying to perform bad action on a good bot that's completely innocent, should be caught by the classifiers in the infrastructure. And so one of the things we've been experimenting with is how to use Dub as a platform to provide a social level, system level test of the classifiers to essentially check that this action here is not possible. So that's a natural use. We can think of social testing as a level of abstraction in testing that resides above system level testing. So we have unit testing where we're testing inside the product. We have end-to-end testing where we test the whole product, but typically with a single user. Social testing using a platform like Dub is more like a kind of level above end-to-end testing where there are multiple users and we're testing not for bugs in the platform, but for behaviors that one user can do to another using the platform and then trying to adapt the platform so that's not possible. So I said that we might adapt the platform so that's not possible, and this takes us on to the next topic of the talk, which is the idea that we could try and detect these behaviors, and we use our technology with Dub, web-enabled simulation, to try and detect whether our classifiers detect bad behavior. But the other thing is, wouldn't it be better if we could perhaps prevent this bad behavior without having to be able to detect it? There's an interesting question here on the research side, which is that maybe it's possible to prevent certain classes of behavior without necessarily being able to detect them. There's an analogy with static analysis here, where it's possible to remove side effects from code without necessarily being able to detect side effects. In fact, detecting all side effects is not decidable, but it's not necessarily the case that you can't get guaranteed to transform a program to a side effect-free version. So maybe by analogy, a similar principle applies to prevention and detection. Maybe we can prevent these behaviors without necessarily being able to detect them. And that's very useful if we're trying to prevent behaviors we've never seen before, but we can define as bad. So I want to give you an analogy to illustrate our approach to this. So suppose it's a lovely sunny day and you're driving along at a moderate speed, enjoying the sunshine, listening to the birds singing, and suddenly straight past you somebody zooms past. They've gone way past the speed limit. They've almost knocked you off the road. They're behaving in a very reckless way. What can you do about this? Well, as the driver of the camper van, not much. You can curse, you can use a different road next time, but there's not a lot you can do. However, as the platform provider, as the people who build the roads, you do have some options. And those options fall into the categories of detection and prevention. So detection, in the UK, we use speed cameras that look like this. They're painted yellow because although the goal is detection, we also want them to play the role of prevention. So when people see these bright yellow boxes, they will tend to slow down. That's the thinking. But the problem is, notwithstanding the slowdown effect of the yellow camera, once the camera's taken its photo and it's detected someone speeding, the bad behavior has already happened, and so we haven't really prevented it. Alternatively, we could put speed humps in the road. Drivers don't like speed humps very much because even when you drive at a normal speed, they can damage the suspension of the car, they increase the wear and tear, they might make a normal journey less pleasurable, even though you're not speeding. But software is different. So just as we said, like if we're simulating an aircraft engine, we can't simulate on the real engineering material. When we put the software equivalent of speed humps into software systems, they can be so much more subtle and sophisticated than the rather crass and crude great big lump that you see in the road that causes you to slow down in your automobile. And we call this mechanism design. Essentially, our bots communicate through a mechanism with the platform. That mechanism constrains their actions and observations, and the mechanism can be tuned with these speed humps. So conceptually, here are our bots who are being rewarded for crawling. They're performing these actions and observations on the real infrastructure, but in between that real infrastructure and the bots, we can impose these speed humps, things like rate limits, transformations on the parameters to particular back-end calls, modifications of the behavior of observations and actions that the bots can perform. Now, we could have done this by simply just changing the infrastructure every time we want to try a different intervention, a different kind of software speed hump. But you can imagine with hundreds of millions of lines of back-end code and tens of millions of lines in the client-side code, the small change you do to implement, say, a rate limit on what a bot can do would be very computationally expensive. Rebuilding the system, worrying about whether that change is actually going to affect anybody else, keeping it isolated from production, and so on. What we would be doing would be genetic improvement. We'd be essentially changing the infrastructure and using the bots as a fitness function to try and assess how good that change is. So to achieve that genetic improvement idea, philosophy, if you will, then rather than directly implementing it on the infrastructure, we implemented at this mechanism layer. So we have a layer in between the bots and the infrastructure, which you can think of as a kind of a constraint vector. So each bot has its own constraint vector, its own mechanism. And by choosing parameters for this mechanism, we can constrain how the bot interfaces to the infrastructure at the back end. So how does that work? So suppose, for example, this bot here can only send 4 messages per minute. It can only see 12 messages per minute, and it's got some other limits of 17. Maybe it can only make 17 friend requests a day. So each bot has a different set of rate limits, different set of mechanism parameters, if you will, and we could imagine mixing and matching the constraints that apply to each bot. So maybe the third bot takes its first parameter from the second bot and its second parameter from the first bot. So those who've been doing research and practice on evolutionary computation will see immediately here that there's the potential for using evolutionary computing algorithms to essentially search over the space of these constraint vectors using mutation, crossover, all the things that we're familiar with in evolutionary computing. But the nice thing is these bots are all can be, they don't have to be, but they can be independent of each other. And so each is giving a signal for its ability to achieve its goal and the ability of the constraint vector to inhibit its ability to achieve its goal. So if we just run this approach, we said, okay, what's the constraint vector that would stop these bots achieving their goal, the bad harmful behavior that we've trained them to achieve? then very quickly we'd arrive at the conclusion that we should set our constraint vector to the lowest possible values. So, for example, you can send 0 messages per minute. You can't make any friends. So essentially shut down the entire ability to interact with the back-end infrastructure. So actually what we need is not a single objective approach, but a multi-objective approach. We have bots that are trying to achieve bad ends that we train to do that to other bots through the real infrastructure, but through this constraint vector. And we have other bots that are trying to achieve perfectly normal, innocent behavior, like a simulator bot that's just joined the platform and wants to make some friends. And now our problem is find that constraint vector which has no impact on the bots that are trying to achieve the normal behavior, but does tend to impede the ability of the bots that are trained to achieve bad actions on each other from achieving those goals. So this is like this speed hump analogy I was talking about, except where someone's speeding, the speed hump should actually prevent them, but where someone's not speeding, they should not notice. They should not notice this on the road at all. Although that's not possible in physical engineering materials like road construction, in software, infinitely more subtle and sophisticated, maybe we can find that ideal setting. So, of course, the constraint vector is all the different ways you can tune the interactions between bots and the real infrastructure, or thought of another way, it's all the ways we could modify the products such that they behave slightly differently and in a way that would tend to inhibit bad behavior and promote normal behavior. So it's not really just three constraints, it's an enormous search space. And that specific speed hump, that subtle software speed hump that has that tendency to reduce harmful behavior and promote good behavior might be kind of like just 1 or 2 or 3 very specific values in this enormous search space. So finding it seems very daunting and challenging. You could think of the search space as an enormous haystack, and our job is to find a needle within it. But fortunately, the software engineering community in particular, and the optimization community in general, have, at least for 20 years now, been exploring and researching techniques that are good at finding needles in haystacks. And that area is this area that's come to be known as search-based software engineering. Essentially, take your software engineering challenge, formulate it as a search problem such that you have a space of individual solutions far too large to enumerate, make a fitness function or possibly several fitness functions that capture the good and bad things you want in your engineering solution, and then formulate these fitness functions as objectives, most often as multiple objectives which are competing and conflicting with each other, as they are in our case. So we have at least one good objective. Normal users should be able to use the platform in a perfectly normal way. We have one bad objective. Bad actors shouldn't be able to achieve their harmful behaviors. Through this mechanism, which is then the search space for which we search for these software speed humps that will have that possibility. So we call this mechanism design. The goal is to ultimately to automate, using SBSE, the search for mechanisms that will have this property. What we're doing at the moment is building up the infrastructure for this. We have the current status is that we can train the bots in those 3 ways I mentioned. We can simulate behaviors of interest, and we can model simple mechanisms. And I'm very excited by the way this project is developing and the possibilities it has for tackling a number of related problems. I've talked a lot about how this applies in social media applications, because that's the company in which we're developing the technology. But we firmly believe that because many organizations now have these 2 properties, that they use the web as a platform for delivering many products and services, and users can interact with each other through the platform, then the ideas that we're experimenting with in web-enabled simulation may well apply beyond just Facebook. You can think of it as a kind of testing, if you will, which is like social testing. So as I say, we can think of end-to-end testing as the interaction between a single user and the product, but the whole product end-to-end, as opposed to the unit testing, which is more focused on individual units inside the system. But social testing is kind of one level of abstraction higher still. It's not a single user using the system end-to-end, it's multiple users using the system end-to-end, and the testing is the interactions between those multiple users through the platform. So it's a relationship between user, platform, and other user, rather than the end-to-end testing case, which is a relationship between user and platform alone. And I think this idea of social testing is also one that applies way beyond just our work at Facebook. The other thing is, I mentioned that the reinforcement learning case is very related to AI-assisted gameplay, and I've talked about search-based software engineering. Of course, we're talking also about simulation and modeling. You can imagine that multi-agent systems are very relevant to our work. Also, we talked about how the bots move around in the social graph. So graph theory is important to us. Various fitness functions that we might measure would involve all sorts of interesting possibilities. For example, information theoretic measurements and so on. There are many interesting and exciting research topics which all essentially come together in order for us to be able to solve the kinds of problems we face and the kinds of problems we want to tackle using web-enabled simulation. So we, as a company, although we have considerable scale and resources, we don't think we can solve all these problems ourselves. We firmly believe and want to reach out to the scientific community for a two-way dialogue, really. I mean, we think that we have some interesting new research challenges, perhaps some old challenges that are already tackled in the literature but thought of in new ways, and some actually new challenges like social testing, which I don't think has been considered in the literature on software testing, not to my knowledge anyway. Please point me to literature if I'm wrong on that. And so, as we've done in other projects at Facebook on static analysis with Infer and on software testing through the Sapiens project, we want to reach out to the scientific community, and we want to do that in multiple ways. And one of those is that we have a current call out for funding. So the funding call has a deadline of July the 15th. So the academics may be thinking, geez, July the 15th, that's pretty soon. But I'm here to tell you that this is a really light touch process. Okay, I think our goal here is to be the lightest touch process we can think of that is still meaningful as a review process. So you only have to put in a 2-page proposal. And if you're successful and you are awarded one of these grants, it's given to you as an unconstrained gift. So we make absolutely no constraint on how you spend the money. Your university may make constraints, but when we give the money to the university, we make no constraints at all. It's untyped money, essentially, that you can spend on your research in the way that you see fit as a principal investigator. Now, it's not the biggest grant you're going to get. Most people have national or international funding bodies that offer considerably larger grants. But it is, I hope, you'll find the lightest touch proposal writing process, and the award is with the fewest possible constraints. So we want to be able to essentially stimulate the research community to consider the kinds of challenge that we're talking about here. And there is a research paper that talks about these challenges that's linked from the SEMLA website, so you can go and find the paper. It's available without a paywall. It's completely open access. And that paper on web simulation by myself and my co-authors in the London probability team sets out this research agenda I've been talking about here in more detail, points to a lot of the related literature, and would be a good starting point for anybody who's considering applying for the funding. I would stress that if your research area is relevant, and you know it is, but it's not listed in our paper or something, please don't be put off. It will be our goal to consider eligible and how can I say, qualified. Your work will be qualified and considered if it can tackle any of the problems that we talk about on web-enabled simulation, or that you think we might face in this research agenda. So that's what we're working on at the moment on web-enabled simulation. I think it's a very exciting research area that will allow us to tackle a number of very interesting problems, and I look forward to talking to you about it and hearing your questions in the Q&A session. Thanks very much for your attention.
Thank you. Thank you very much, Mark, for the exciting topic and exciting talk. So we have a couple of questions in the Q&A. Maybe first start with one question from Marius. Marius is curious about how this new approach relate to cow engineering, like this approach of social testing with agent on the platform, how this relate to current cow engineering techniques in the industry.
Sorry, what's cow engineering?
Yeah, cows engineering, where they actually try to stretch the platform to uncover potential weaknesses in the platforms and discover issues in production.
Well, you could use this approach for stress testing because we have these bots. So we could just make lots of bots, and the more we make, then the more it becomes like stress testing. So it's definitely possible to use web-enabled simulation as a platform for stress testing, but it wouldn't necessarily be. You know, it's better if you were training the bots to do something interesting. And usually in stress testing, the user behavior you're simulating is just demand resources as much as possible. So it may be that there would be better platforms for stress testing than web-enabled simulation. But if we then recast what we mean by stress testing a little bit and say, instead of it just being make the most resource-hungry thing you can think of, if you say, what's the most sophisticated, low-resource stress test, in the sense that you actually don't require a lot of resources, but you do put stress on the system nevertheless, that might be an interesting thing to look at with web-enabled simulation. So essentially we haven't done research on this, this is just speculation, but I imagine if you had a web-enabled simulation platform, then you could train your bots with search-based software engineering as a guide, where the fitness is to consume as low, to have the lowest amount of resource consumption, but the highest amount of impact on the back end. So maybe you find those kind of, this might be very useful for use cases where one is interested in trying to prevent denial of service, very sophisticated denial of service attacks that wouldn't normally be detected as heavy overuse of the system, but might be more subtle. But for regular stress testing, I'm sure there are better platforms for that than what we're talking about here.
Yeah, thank you. So we have another quite popular question from Saidu Rahman, who is mostly concerned about the cost of using evolutionary techniques for this type of work. How do you deal with it, particularly in your context, in terms of scalability?
That's an interesting question. So, I should call out right at the start here that we're currently still building the infrastructure to enable us to be able to run things like evolutionary algorithms on the search. So at the moment we can model the bot's behavior, we can train the bots, we use a variety of machine learning techniques to train the bots. We are working currently on making sure that their behavior in simulation does correlate strongly with what we see in production. And we're working on building out the infrastructure that allows us to do this at scale. So I haven't got results for you right now on evolutionary computation. I firmly hope that by this time next year we would have results on SBSE applied to this problem. But the good news here is that each bot can compute a different fitness and can compute multiple fitness values as it's doing its work. And we can have tens or hundreds of thousands of these bots. And the kinds of problem we're trying to tackle don't require instantaneous response. So if we want to try and find a mechanism that will tend to promote a certain behavior and inhibit another, we can search for that for some period of time. And of course, the other thing is that we have an enormous server farm where we can scale up any problem that is easy to parallelize. And guess what? It turns out that evolutionary algorithms are just such a problem. So evolutionary algorithms are often referred to by their adherents as being embarrassingly parallel. Essentially, you can farm out the fitness computation in parallel, and therefore a cloud-based infrastructure like the one that most tech companies have, and we certainly have at Facebook, is ideally suited to this problem. So I can't give you results at the moment for that, but we're currently building the infrastructure which will make exactly what the questioner is asking about possible. And I think also there may be some interesting new, I've only thought about this, I haven't actually done the engineering work and the research, but I get the feeling that we may actually throw up some interesting new possibilities for techniques like evolutionary computation, because it's the bots that are computing them, and so concepts like generation may evaporate, and we may have a kind of on-demand fitness. When the bots learn something it's worth knowing, it kind of signifies that, and you can have some kind of messy GA that computes the overall evolutionary trajectory. So I think there'll be more research questions to come and more exciting work, but I'm not at this point anxious about scalability. I must say I'm not, based on what I've seen in the infrastructure we've been able to build so far.
Interesting. So we have another popular question regarding the proposal call. Actually, it's from Eddie and Matty from University of Calgary. So his question is, given that the WWL simulator and the mechanism algorithm are not publicly available, how exactly can we research or propose something realistically helpful? It is also.
That's a very good question.
Yeah.
I'm going to put the proposal in as an answer to a question. I apologize to Lauren McGinn because I'm answering your question with the proposal URL, just because I can't find another mechanism on Zoom that just allows me to post an arbitrary chat message. But there's the full proposal text in answer to the most recent question I saw. And we do address this in the proposal call itself. You'll see that we're saying, well, if you're funded, we'll give you an unconstrained gift. So there's absolutely no constraint on you to actually tackle problems for our specific web-enabled simulation. You could build your own, you could use open source, you could pick a related problem where you can imagine there's a platform and users interact with each other and you're going to search for mechanisms that promote one behavior and inhibit another. We're interested in the fundamental science. We're not using this funding as a mechanism to try and get people to actually work specifically on our infrastructure. We want people to do the basic science, to answer the fundamental scientific questions. And those questions are by definition and should be agnostic about which particular platform and which particular technologies. So please don't be inhibited or by a perceived need to apply your techniques to Facebook-specific web-enabled simulation. We actually would encourage you to consider a wide variety of other possible applications of the ideas of web-enabled simulation, and to use whatever evaluation mechanism is most suitable for the kinds of research question you want to tackle. As long as we can see how those fundamental scientific questions are addressing the kind of questions we're raising in the paper, then it's absolutely on topic for us.
Thank you. Thank you very much for that. We have another question from Eugene Siriani from University of Montreal. He's excited about the talks. And he has a question regarding when, in your opinion, you think evolutionary algorithms are more appropriate than advanced machine learning algorithms like neural networks.
That's an interesting question. I think that to some extent there isn't really a dichotomy between the two, because many advanced neural network techniques use evolutionary algorithms under the hood, and you can also, vice versa, you can use fitness functions that are actually also classifiers, that are, trained as machine learning. So I think that really, obviously, if you have a fitness function you want to optimize for, then that means that an optimization approach rather than a classification approach would be suitable. So that might put you in the ballpark where you start considering evolutionary algorithms. But I think there need to be a few more questions to which you'd answer yes first. Just because your problem's an optimization problem doesn't mean you necessarily want an evolutionary algorithm. I'm a firm believer in simple techniques like hill climbing, gradient descent, essentially, even greedy algorithms where they work. Often it's a mistake to leap in and use the most sophisticated technique first. In fact, it's almost always a mistake. It's much more sensible to use a simple approach first. So if you have a fitness function to optimize for, I strongly would recommend using something like a gradient descent, simple hill climbing type approach. that will give you immediate feedback on what your search landscape looks like. You'll understand, how many plateaus they are, whether they have similar size hills, whether they're big basins of attraction, all these kinds of things immediately fall out from using that approach. And evolutionary algorithms are only really valuable where, if we're talking about evolutionary algorithms in the sense of genetic algorithms, then where you're using crossover, you need your problem, as Melanie Mitchell showed us, to have this so-called Royal Road property, which is essentially saying that crossover will tend to find better solutions from two adequate solutions, rather than, as other theoretical work has shown, crossover is very disruptive as an evolutionary operator. So many problems do have this kind of decomposable property to them that leads to a kind of Royal Road property, but many don't. And in software engineering, I think sometimes we've made some missteps by sort of using evolutionary algorithms just because they're the most exciting sounding technique, but not necessarily thinking scientifically about whether they're the most appropriate technique. But I think the question was also, when will we use evolutionary algorithms and not, say, neural networks? And I think that's a bit more fundamental. Like, if it's a classification type problem, then neural nets would fit. But I think that's obvious. So maybe that wasn't the intention of the question.
Yeah. Thanks. We have another question from Puyan Jamshidi from University of South Carolina. Okay. So he mentioned that in the web-enabled simulation, you mentioned that the bots have some intrinsic reward functions embedded in them. But he's thinking that if we let agents learn the reward functions by themselves, this may result in discovering new bugs that you never encountered if you embed a pre-specified reward function, and eventually there will be some emerging behavior. What's your thoughts on this?
So we have to specify something, don't we? I think. If the bot is learning the reward function, then how do we know whether it's learning a good reward function? We'd have to have some kind of meta reward function that is, and unless our goal is merely diversity, maybe, for example. So we want the bots to explore as widely as possible, and then you could say the only constraint we have is that they should do things that other bots aren't doing, or something like that. There's lots of possibilities here. I must say, for mechanism design, which is what I've been particularly focused on, as you can imagine, there's the strong SBSE connection there. It's not so much the bot behavior that needs to be very sophisticated, but the ability to search mechanisms. The bots are the fitness function for the mechanisms. So we want the bots to be simple, at least computationally tractable. And for that scenario, the more sophisticated techniques I talked about, like reinforcement learning, may not be the most appropriate, certainly not in the first instance. Something that's a bit more rule-based, maybe with some machine learning to guide the choices that are made when there's choices to be made, but that can be computed quickly, is very valuable, because what we want is, for each mechanism, we want to run bots, see how they perform, and use that to assess the quality of the mechanism. And the real mileage that's gained out of the approach is searching the mechanism space, not searching the bot behavior space. So long as the bots are sufficiently realistic that if we say this mechanism is better than that mechanism, then in simulation, then that's going to carry over to production. That's all we really require. So the bot's behavior has to be somewhat maybe typical, or it has to be like an extreme case, like an upper bound in some situations. It has to be realistic, but only realistic enough that final scientific claim that this mechanism is better than that one in simulation implies it's better than that one in production holds. And that doesn't necessarily need the most sophisticated techniques. Okay,
so there is a related question actually from Carlos Gavidia Calderon, which is concerned about how is it related. So how are constraint vectors that you're using for the bot relate to the users of Facebook? Like, how are there any consideration in bot design that approximate their behavior to humans? That's kind of related.
It's a very interesting question, Carlos, and congratulations on getting your PhD last week. Great result. So this is something that intrigues a lot of us in the team and intrigues a lot of the people we talk to. It's like, essentially, you could pose it as the Turing test type question, isn't it? It's like, well, how clever can the bots be, and how much do they actually simulate a real person, and so on? And there's a lot of very interesting research on chatbot for example, there are papers that argue that chatbots already kind of passed the Turing test. Some of the chatbots I've spoken to certainly didn't, but I'm told that they can. So this is a very interesting question, but I come back to the answer I gave earlier, which is that certainly for searching for mechanisms, the thing I focused on in this talk, we don't actually need the bots to simulate people very faithfully. What we need is for a group of bots as a community to behave in statistically similar ways to a group of people. So just as if I say my job is to model exactly the journey you would take when there's no COVID-19 to get from home to work, then modeling that precise journey and all the decisions you make is quite a hard problem. But if I say I now have to model the flow of people and traffic and commuting in London in a normal situation, non-COVID, on a typical Monday morning at 9 a.m., then that's a much easier problem, statistically, scientifically, technically. It's much more tractable to try and capture these gross statistical properties at some sort of coarse granularity than is to faithfully model individual human intent and behavior and beliefs and so on. So when we talk about modeling users with bots, we're talking about that more statistical emergent property. And that solves a lot of problems for us. One is it makes the problem technically more tractable, and that's good because there are plenty of challenges already, as you can see in this research agenda. And the other is it means that when we're training the bots, we can anonymize the data. We're not interested in simulating a particular user. We just want to simulate a whole kind of class of user behaviors. And so it's easy to anonymize the data, to train the bots, and to talk about these gross statistical emergent properties.
Okay. So Puya Jamshidi has another question about, he's curious about how the research in causality and causal inference relate to this simulation environment.
That's a very good question. Thank you very much for that question. Yes, so causal analysis is a very, very interesting topic. There's been some very exciting research on this, and it's actually started to find its way into software engineering research too. There have been some papers, for example, on how you would use causal inference in testing. There's obvious kind of causal, you want to understand the root cause of a problem. And it's also been used in things like App Store analysis, where the goal there is to say, hey, we release all these different versions of an app, but and we noticed that the ratings for this app went up at a certain point, but was it really caused by something in that release, or was there some other factor? And there's been research in the literature on this. So the question is, how would it apply in the web-enabled simulation framework? So one interesting causal question we have is like these kind of counterfactual questions. What would the simulation be like for this not to happen? Is a fundamental question we're asking, and also a kind of backwards causality. So what would the initial conditions have to be like in order for the simulation to get into this state here, this state that we don't want it to get into, maybe, or maybe some state that we do want it to get into? So in general, the ability to go beyond correlation and to talk about causation is definitely going to be relevant to our research agenda. In many situations, we won't have that problem because, the problem of correlation versus causation, because we'll know we're doing a very specific intervention and we'll have the kind of before and after that we can compare. But in other situations, particularly where we're trying to infer things over a long period of time in a counterfactual way, then I think causal reasoning will have a role to play.
We have another question about privacy, and I would chain this in. I understand that the platform is still trying, but Professor Roy from Saskatchewan, it's concerned about privacy issue. How well the privacy and fake account issue were dealt with for the bots? We see a lot of issue with privacy. Also, there are a lot of fake accounts. He said, of course, the talk is more general, but he's concerned about what he wants to know about how these aspects are taken into account when building this simulation environments, and how these people tackle those issues. Yeah.
I'm trying to understand several aspects to this, so I'm not sure quite which one Chancel's got in mind. It could be the privacy, as in we're training these bots on data. So is there a privacy issue there? And I want to stress, as I say, that we're training them on anonymized data to emulate gross statistical properties, emergent properties of whole classes of users. So there's no privacy issue there. At least I don't believe there is. Another issue you could argue is you're relating to these fake accounts. So these bots essentially are fake accounts. I mean, they're not real users, right? So they're bots, and that's not something we normally encourage on our platform. So in fact, we have teams that whose whole job it is in life is to stop such accounts. But of course, these are our own. we are allowed to use our own platform in the ways we choose, particularly if that's going to help us to try and find issues that might tend to hurt the experience of real users on the platform. And so we keep these bots separate from production, and the fact that they are kind of bot accounts doesn't really matter. In fact, many times we can implement them without actually having to have the bot use a real user account. It's not even a real user. It's like a kind of a shell that doesn't have to have user properties, but just has to be able to do the kinds of things that users can do. I'm not sure that's answered the question, because it seemed very high level, and I wasn't really sure exactly which angle that the question was coming from, but I've taken two possible ways it might have meant. I hope I've answered your question.
I think ZU has somehow the complementary question, maybe more on an adversarial perspective. His question is, can we actually train the bots to avoid being detected by adding penalty in the reinforcement mechanism? Like, as you're simulating this environment to detect issue in the behaviors of the users, can on the other side train similar bots to avoid and evade what you're actually trying to accomplish?
Yes, I think this is a very interesting question, and certainly something we've thought about. We haven't, as I want to stress over and over, this is a research project at this point, but it's a research project which is in industry. So we're expected to be very applied research and to have results soon. Within a year time frame, we'll be in production. So one of the things we found when we started this research agenda is actually there are a tremendous number of possible applications for a web-enabled simulation. Exactly as you alluded to just there, like if you have a platform that can have bots that are trained using reinforcement learning, then a natural thing to do would be to train them to try and evade detection and then see how good the classifiers are at detecting them. And to set up a kind of an arms race so that we can get ahead of many of the problems that we see on the platform, maybe even tackling problems that we haven't seen. And this is useful in two scenarios in general. One is where developers have made changes to the platform, which of course happens all the time. So every time we make a change to the platform in a logic sense, we're moving into a new possible world for which we haven't got 100% accurate training data, because this platform is now a new version of itself. And that's of course happening all the time. There are 100,000 more commits every week to the central repository. So the scale of change is enormous, and therefore having the ability to train bots to behave in ways that we haven't seen in an adversarial setting, as the question asked, is very valuable. And of course, the other thing is to head off problems that we haven't yet encountered, but that we might encounter, to essentially get ahead of the harmful behaviors that might possibly at some point be deployed on the platform against other users, by other users, but that haven't yet been witnessed. And so we can imagine that the evolution of the mechanism design approach, and this is something that's very much research speculation at this point, but to give the biggest possible projection, if we bring together this idea of mechanism design as a search space to search for improvements to a product, to encourage certain workflows and to discourage others, and then we imagine those harmful workflows being adversarial, and we train bots to be adversarial, then we can imagine a very interesting, scientifically co-evolutionary adversarial arms race in which we try to find mechanisms which are not only good against the behaviors we've already seen and we've trained bots to perform, but mechanisms which will be good against all comers, including those we've never seen before and those that we haven't even anticipated and that haven't been witnessed in production before. So I think that you can imagine, once you've got an infrastructure like this, the kinds of research question you can ask and the kinds of application and use cases to which you can apply it are really enormous. And scientifically and intellectually, the possibilities are very exciting, and I think could stimulate a lot of future research.
Thanks. We're almost running out of time, but let's pick some few more questions. We have a question from Professor Menzies about the call. His question is, if we are funded, can we access your infrastructure to do those?
So if you want to actually work on our specific infrastructure, there are different mechanisms for that. So we have contractor projects. People can do fellowships, contracts, and PhD students can do internships. And all three of those routes would allow people to come and work in the company like other employees in the company alongside existing teams, and will get access to the infrastructure through those mechanisms. The funding call, as I mentioned earlier, we specifically want to fund the basic science. So we don't want this to be seen as us trying to say, solve our problems for us in a kind of engineering way on our platforms, but more take this general scientific research agenda that we're setting out, and using your existing research expertise or areas that you're currently thinking about in research, maybe think a little bit about how those could be used to tackle those kind of fundamental scientific questions. So the questions we talked about, like, how to train the bots, how to find the mechanisms, what kind of algorithms we should use. These are all very generic scientific questions for which you don't need to actually evaluate on our platform. We can translate the results from other platforms or other domains. If, on the other hand, if your goal is to come and work at Facebook on our infrastructure, then by all means put in a proposal, but don't feel the need to warp your proposal towards that. Rather, if you're a PhD student, think about doing an internship. If you're a professor, full professor, as Professor Menzies is, then maybe either think about contract work or think about putting one of your students into the intern program. That would be a better mechanism.
Maybe one last question about evaluation by Professor Eddie and Matti, related to evaluation as well. He's actually wondering whether or not in a large-scale online social network like Facebook, it's possible to run a bad behavior detection algorithm on any kind on the entire network, or it must be done offline or in a slide of network, like how this type of research can be evaluated on this platform.
Yes, it's not the area that I'm specifically working in myself, but there are whole teams whose whole job it is to design these classifiers to detect those behaviors. Our job in building the DubDub platform is twofold. One is to act as a way of testing those detection systems by simulation, and the other is to find mechanisms, as I say, through this mechanism design approach, such that some of those behaviors become harder to achieve. So essentially prevention rather than detection. But yes, there are, I mean, this is a huge research area, how one detects and classifies these kinds of behaviors that are undesirable, and tries to stop them before they actually hit other users.
Thank you very much, Mark.
Thank you very much, everyone, for your very interesting and astute questions. I enjoyed having the conversation with you. I hope everybody is well and safe.
Thank you very much, everyone, for attending SEMLA webinars. I hope you enjoy them. I encourage you to come back to the website. We'll post all the recordings, the slides on the website, and all the material that we collected through this webinar. Thank you very much, and have a good day.